Okay, so today's lecture we'll start with the network layer, and what I'm going to do is we'll start off with an introduction to the network layer. What are the principles, fundamental principles involved in the network layer, and then we'll deal with routing. Routing is one of the main functions of the network layer. So before going into the details of how routing works, or how a router works, and how routing is implemented on the internet, we'll look at the problem of routing as a theoretical issue and look at algorithms that compute good routes. So I'll change the order of topics from the book. We'll start off with the introduction, and then we'll get into the details of abstract algorithms for routing, and then we'll get into how routing is implemented on the internet. So when you were doing your programming assignment, and when messages were going from user A to user B, they were going through the CVRs, right? So when these packets were going through, or the messages were going through from user to CVR to another CVR to the user, what was the CVR doing? Well, in our model, all those CVRs were connected to each other. We had a full mesh topology. Each CVR through that table knew the exact location and identity of the other CVRs. So if you had to send a message from this CVR to this CVR, there was a direct logical connection between the two, and this CVR simply forwarded the packet to the other CVR. Now suppose if we did not have a full mesh topology, so now you're trying to send a message from this CVR, CVR A, to CVR B. CVR A does not know or does not have a direct path to CVR B. The question is, how are you going to send a message from CVR A to CVR B? So up until now, what we have dealt with in the application layer or in the transport layer, you always assume that there was a direct connection between the entities that were talking to each other. Either the process was talking to another process, or the sockets were linked directly. Now if there is no direct connection available, you have to somehow send a message from here to there. The network is connected. There are paths available. So how are you going to send the packet or the message from here to there? Yeah? Okay, to another CVR. So which CVR are you going to choose? Shortest path? So the answer is choose path That is shortest path, that's what you're saying? So which in this scenario, which CVR would you choose? You could choose this one or this one. So depending on which is the shortest path. Suppose through some computations you decided that this one is the shortest path. Then what you're going to do is you're going to forward the message or the packet onto this link onwards to the final destination. So this operation has two parts. One is forwarding on the right link. You have a number of different links available, number of different output links available from this CVR. So forwarding is one aspect of that. And then the second aspect is choosing which of these links should you forward it on. So forwarding and choosing the right link or the right path, they are related but they are different. And routing deals with choosing. So routing chooses the right path. So when we come to the details of how a router on the internet works, you'll see that there are different problems associated with forwarding and routing, and they can be separated out. But often people get confused between forwarding and switching and routing. Routing is the process of computing or identifying the best paths. Forwarding or switching is sending those packets onto the best path. So these are both important functions of the network layer. So the application layer and the transport layer, they are implemented on the end systems in a network, but everything from the network layer down is implemented on all the elements of a network. So in the core of the network, you have to implement the network layer, its own data link layer, the physical layer. But inside the network, you don't implement anything of the application or the transport layer. So all nodes, whether they are end hosts or routers within the network, they all have to implement the network layer. So this seems to suggest that your end host, like a workstation, also implements this network layer functionality. Is that right? Just remember, what are the two most important aspects of the network layer? Forwarding on the right link and choosing the right link. So you're sitting with your laptop, you have a wireless connection. You can also have an Ethernet connection. You can connect to the local LAN. So when you have two connections, then your workstation or your laptop has to decide whether to send the packet out on a wireless link or on the Ethernet link. So every end system also has to implement both routing and forwarding. But within the network, routers don't have to implement anything about the network layer. So if if you're sitting with your laptop, and suppose you have an intelligent routing mechanism built into your laptop, you have an Ethernet connection and you have a wireless connection. Which connection should you choose to connect to the internet? Suppose you're trying to connect to CNN.com. You have an Ethernet connection and you have a wireless connection.
I suppose we choose the LAN because it's more reliable. But then again, like some other heuristics, like which is more throughput.
Okay, so you're saying reliability is an issue. So your mechanism will choose something which is more reliable. So how does that gel with what was said earlier, that you have to choose the path that has the shortest distance?
Okay, we're assuming that the next hop is really about the same distance using the LAN and the wireless.
Yeah.
So we're not really choosing the shortest path at this point.
But still you sort of expect, or your intuition tells you that you might choose the LAN.
Yes, because it's sort of guaranteed with a interference.
Okay. So that gets into the question of differentiating between these two links. Your first hop, you might have the same number of hops, but your wireless link is sort of unreliable. Your Ethernet link or the LAN link is reliable. It gives you better throughput. So what you can do is you can assign costs to different links. And what your routing algorithm would then do would choose the shortest cost path to your destination. So your different links might have different costs, 3, 7. And these costs could be anything. They could be what you want it to be. Cost could be the delay on a particular link. It could be the throughput on a particular link. It could be the loss rate on a particular link. It could even be the physical cost or the actual dollar cost of using a particular link. Suppose your wireless connection is through some Sprint or T-Mobile that charges you per byte, and your Ethernet connection is a flat rate one, then clearly the cost of the wireless link is going to be more than the Ethernet link. So you can define costs in a variety of different ways, and the job of the routing algorithm is to choose the right path given your cost constraints. And once the path is chosen, then forwarding takes over and you send your packet on to the right link. So forwarding is moving packets from router's input to the appropriate router output. In this case, our router was the laptop. It could be any general node on the network. The node has a variety of input links. So in the case of the laptop, the input link was only one link, that was the transport layer of the laptop handing over packets to this laptop. In the case of a general router on the internet, it will have multiple ingress links and multiple egress links. So you will have packets arriving from different input links which have to be forwarded to the right egress or output link. And things can get very complicated in that forwarding process. We'll see that later. So routing is the process of choosing the right path, and forwarding is actually implementing sending those packets on the right path. So the interplay between routing and forwarding is explained in this slide. You have routers here that are connected in some sort of topology. A packet arrives with a particular header. So now we are not defining what this header signifies. It could be the IP address, it could be some virtual circuit, or as in the case of the CVR or programming assignment, it could be the location of the remote user. The point is that this header is identifying what's the final destination of this particular packet. And based on this header, this router is going to choose which of the output links to send the packet along. So the way it's implemented is you have a routing algorithm, which is a separate process, is going to compute the best routes, and it will set up a local forwarding or routing table. And the routing table is a very simple lookup kind of data structure. Given the header value, which output link is to be chosen. So if you change the header value, you're going to forward it on to a different link. This header value indicates where it's going, what the final destination is, and depending on that, a choice is made of the right output link. So let's come back to the problem of routing. So here you have two nodes, A and B, that are trying to communicate. A is connected directly to this router R1. The question at router R1 is, if the final destination is B, which is informed through the packet header, what should I choose the next hop to be? Should it be R2 or R3? Now, as we just explained, these different links in a network can have different costs, and the job of the routing algorithm is to determine the route from A to B that will minimize the cost, the path cost. So here these costs could refer to the delay on a particular link, it could be the loss rate on a particular link, or it could be the inverse of the bandwidth of a particular link. The more the bandwidth of a particular link, the less is the cost. That's better for your connection. So suppose you have a network like this. Then which is the path that R1 should choose to go to B? So 1 to 2, 2 to 5, 5 to 8. That seems fairly, that seems right, and you can sort of check this by inspecting, right? This seems to be the right path, and you can just look at the network, inspect it, and choose the right path. Is this inspection solution scalable? This is a snapshot of the public internet in 1999. It has exploded much more than, beyond that. There's this company called Lumeta.com. They make these nice internet graphs or internet maps. So this is an example of what the internet looked like in 1999, and all the nodes here actually don't represent n nodes but autonomous systems. So how do you choose a path from, let's say, sitting at Columbia going to CNN.com? Yeah.
Treat, you can group the internet into smaller pieces, as opposed to treating it as each node as you group collection of nodes into groups and then devise the same algorithm.
So the suggestion is to group pieces into okay, and then
That contains where you're trying to go. To work.
so you construct several such groups and then you try to find the shortest path between these groups. So what you're saying is, and so each group will have multiple machines, and you might construct a path between these groups. These groups might be linked to each other. What about within a group? How do I reach this link from a point in the group? So you're saying, so the answer that you're getting to is hierarchical. So you have one routing scheme within a group and then another routing scheme between groups. That is actually the way that things are done on the internet. And these groups are very naturally defined in the terms of autonomous systems, or the ASS. Like Columbia is an autonomous system. AT&T network is an autonomous system. Rice University is an autonomous system. Your local ISC is an autonomous system. So there is a routing mechanism between autonomous systems, and then there's a routing scheme within an autonomous system. So the way things work on the internet is doing things hierarchically. So let me explain it a little bit more. So there's this website called traceroute.org, and traceroute.org gives you access to public traceroute servers. So what you do is, if you go to a particular you go to a link here, you come to a traceroute server, and what you can do is you can route, you can find out the route that is taken by packets from that server onto any other node on the internet. So let's try the Columbia website address. And you get the result here. So the packet starts from the traceroute server. It goes through all of these different nodes and finally arrives at shadow.cs.columbia.edu, which is the Columbia website. Now, if you notice here, you can identify different groups of routers. So this is the final server. This is the end host. All the nodes between this end host and the traceroute server, they are all routers. And what you see here is you can group these routers into different sets, the way it was suggested earlier. So you have at least 2 Columbia routers here. You have multiple routers level 3. 1, 2, 3, 4, 5. So level 3 is a tier 1 service provider, and the packet is going through multiple routers on the level 3 network. Similarly, yipes.com, it's possibly the tier 2 or tier 3 provider for the end host, and the packet is going through multiple routers in that yipes.com autonomous system or domain. So by doing this hierarchical routing, what you can do is you can separate out the mechanisms within an autonomous system and between autonomous systems. So the way packets are being routed here in the level 3 network, so in the level 3 grouping, packets are going between different nodes. The way that is done, that need not be known or revealed to the Columbia autonomous system. Why is that? Well, there are many different issues. One issue is scalability. If you have millions of such nodes on the internet, then the details of the costs between each node to be known at all the other nodes is simply not scalable. A router on our backbone will not be able to process and keep track of all the costs spread all over the internet. So that's why routing is broken down into this hierarchical system. The details of what's happening within a group are not revealed outside the group. All that is done is a very coarse level routing between groups. And what happens within the group is different. The other issue is these groups may not want to reveal their topology due to privacy reasons or due to security reasons. So if that topology is not known, it's very difficult for another group here to choose the right path. Do you see what I'm saying? If we go back to our example here, to choose this right path, you needed to know these costs. So every link cost had to be known at R1 some way or the other for R1 to choose the right path. On the public internet, autonomous systems are not going to reveal their internal costs to other routers or other autonomous systems. So you cannot implement algorithms like that directly on the internet. So what's implemented on the internet is a form of hierarchical routing. So let's now start looking at how you do routing within a group. So first technique, which is Very simple. It it is this technique of flooding. So what flooding does is, suppose you get some packet on your ingress link, then what you're going to do is simply flood or replicate the packet on all of your outgoing links. So instead of choosing a path, you're choosing all the paths. The advantage of this scheme is it's very simple. You don't have to do any sort of routing computations. Every destination on the network is reachable. You can prove that if your graph is connected, then you can reach every node on the network. Disadvantage is often routers are going to receive packets multiple times, and it could cause a packet explosion on the network. So packets can go around in loops forever. You can imagine that you forward a packet on an outgoing link, and then there's some path which brings back that packet to this router. Then that packet is going to circulate forever and it's going to explode. So this flooding technique does not prevent looping. Packets can go in a loop forever. And thirdly, it's inefficient because you're not choosing the right path. You're just simply trying to send it on all paths. The solution which is used in networks is to find spanning trees. So what's a spanning tree? A spanning tree is a tree. It's not a graph, so there are no loops. And by spanning we mean that all the nodes of the graph are in the tree. So the solution of finding the right route is to construct the lowest cost spanning tree from each of the nodes to the destination node. So let me explain that. So if you look at this destination node R8 and you construct all spanning trees, then the spanning tree that this slide is showing is the lowest cost spanning tree for that destination node. If you choose any other spanning tree, you'll find out that that spanning tree will not give you the lowest cost route to the destination node R8. Now the second question is, how do you compute or how do you build these spanning trees? Yeah.
Well, if you know the cost of the network, then you know the spanning tree cost.
So if you know the costs of the network, then you use Dijkstra's shortest path algorithm. If you don't know the costs, then what do you do?
Then you assume the cost is the same. This way.
Well, you don't have heuristics. You actually have a well-defined algorithm that will do it for you. So the first suggestion, or the second one on this slide, is use Dijkstra's So Dijkstra's shortest path algorithm will build this spanning tree. What are the assumptions behind using this algorithm? Cost should be positive. Well, that we are assuming. Yeah, cost should be positive. More importantly, complete knowledge of topology is needed. So if you're sitting at R8 and you're running Dijkstra's algorithm on this network, if you do not know the cost between R1 and R3, whether there's a link and what cost it is, then you cannot run the algorithm. So to run this algorithm, you have to have complete knowledge of the network at each node. So complete knowledge of topology is needed. So Dijkstra's shortest path algorithm falls under the class of algorithms which are link state and it's centralized So one of the drawbacks of Dijkstra's shortest path algorithm, the two main drawbacks are this complete knowledge of topology being needed, and secondly that it's centralized. In a large network, you can imagine that the amount of information needed at each node is going to be a lot. And a lot of that information is not relevant or useful to compute the routes. But because of the nature of the algorithm, you need all that information to run the algorithm. So an alternative to the link state or Dijkstra's shortest path algorithm is the distributed Bellman-Ford algorithm. The distributed Bellman-Ford does not require complete knowledge of topology. It only requires knowledge of your neighbors. All the computations in the Bellman-Ford algorithm are distributed. So there is no centralized computation of routes. And the Bellman-Ford algorithm falls under the class of distance vector algorithms, not link state. So let's switch to so let's go through what the details of the link state algorithm or Dijkstra's algorithms are. So you have the graph abstraction as we saw earlier. You have a set of routers and a set of links, and our job is to find the best path or the shortest cost path where the costs are given by the link weights between any two nodes. So routing algorithm is the algorithm that will find the least cost path, and the link state algorithm, which is the Dijkstra's algorithm, works something like this. So as I said earlier, the complete network topology and the link costs have to be known to all the nodes, and this is achieved via a link state broadcast. So this broadcast is received by all the nodes. All the nodes have the same information and they act on this information. And at each node, once you have this information, then you're going to build this spanning tree, the least cost spanning tree, which will give you the least cost path from this source node to all other nodes. Once you have this least cost path, then you can construct the forwarding table. So the routing algorithm will then feed into the forwarding mechanism. You first get the right paths and then construct the forwarding table. So this algorithm is iterative. After k iterations, the algorithm is guaranteed to give you the least cost path to at least to k destinations in the network. Another important property of this Dijkstra's algorithm we'll see shortly. So the notation is the link cost between any two nodes x and y is given by C of x comma y, which is, if a link exists, it's equal to the cost which is defined, and if a link doesn't exist, then that cost is going to be infinity. So if there is no direct link between any two nodes on the network, the cost is defined to be infinity. Otherwise, it's the link cost. dV is the current value of cost from of path from source to destination V. This is going to be updated as the algorithm iterates. PV is the predecessor node along the path from source to V. So what is meant by that? Actually, suppose the path to this node V is being computed from this node X, and the path that you compute, so this is Y, this is Z. Suppose this is the path that you're going to end up with. Then your forwarding table is going to say that if I'm at X and I want to send a packet to V, then send the packet on this link to Y, and Y becomes a predecessor node on the path. It'll become clear as we see the algorithm work. N prime is the set of nodes whose least cost path is definitively known as the algorithm progresses. Eventually, N prime has to become equal to N, which is the set of all nodes. The algorithm is very simple. So the algorithm is running at node U. You initialize N prime to simply the node itself, and then you look at all nodes V which are neighbors of U. So, so if this is U, you're going to look at these two nodes, Z and Y, which are neighbors of U in the entire network. So for all the neighbors, you set the distance to the neighbor to be equal to the cost of the link. For all other nodes, the distance is going to be set to infinity. So if the cost is 3 and 2, then D from U to Y is going to be 2. D to Z from Y or from U is going to be 3. And D to any other node, let's say V, is going to be infinity. So you initialize this way, you set only for your immediate neighbors, you set the cost to be the link cost. For all others, you set the cost to be infinity. Now what you do is, you find a node W which is not in your n prime. So n prime, remember, initially it's just the node itself. Find a node such that the distance dW is a minimum. So in this example, that node would be Y, because the distance is the minimum. The distance to Y is 2, distance to Z is 3. So you add your W to the set of nodes for which you know the least cost path, and then you are going to update dV for all V which are neighbors of W, but they are not in n prime. So an example here is, let's say you have this node S and this cost is 5. When you initialize, D of S was infinity. D of T was also infinity, because there is no direct link between U and T and U and S. So in the initialization step, your distance to both of those nodes was infinity. But now when you include Y in your group n prime, then you're going to look at all the neighbors of that new node which you have included in your set, and you're going to update the distance to those neighbors by this formula. It's going to be the minimum of either the current distance dV or the distance to the node W plus the cost of the link between W and that neighbor. So in our first update step, since these distances were infinity, you're going to choose the new distance as the distance to the node there, which is 2, plus the cost of the link between that new node and all its neighbors. Somebody had a question? So you run this algorithm. Now you have a finite distance to a lot more nodes in your network, and you run through this again. Now you look at all the distances and choose node W which has the least cost distance, include that in your set, and then look at its neighbors, and the algorithm proceeds in this way. So here you have an example network. You're running this algorithm at node U. Initially your n prime is the node U itself, you set the distances. Well, the distance to node V. Well, the distance to node V and the predecessor node for V is set here. So the distance to node V is 2, and the link and the node before V to get to V is going to be U. So you set this distance here. The distance to W is 5 because there's a direct link, and the predecessor node is U. Similarly, distance to X is set, and then the other distances are set to infinity. So in the next step, step 1, which is going to be the node which is included in your set n prime? Well, the node which had the smallest d value, and that node is going to be X. Right? The distance to X is 1, the distance to V is 2, the distance to W is 5. So you're going to choose X and include that in your set. So you update that, and now you're going to recompute the distances to all of X's neighbors. And this is where you see the interesting thing happening. Earlier our distance to W was 5. Now once you have included X in your set, you look at all of X's neighbors. The distance to W through X is minimum of either the distance from U to W is the minimum of either the current distance or the distance going through X. The distance going through X is the distance to X, 1, plus the cost of the link between X and W. So now the distance becomes 4, and you're going to update your data structure. You're going to update the distance to W to be 4. And now your predecessor node becomes X, not U. You're not going to use the direct link between U and W. Right? Now in the next step, you can choose, now you have to include another node in your set n prime. So you can choose either Y or V. Both have distances 2. It doesn't matter for the correctness of the algorithm, you just choose one, update the data structures, then choose the next smallest, then the next, and finally you have all the nodes as part of your set n prime, and the algorithm terminates here. So now when the algorithm has terminated, what would a forwarding table look like? So suppose now I want to go from node U to node W. What would the forwarding table at node U look like? Forward to X. And how do you get that information? So the lowest cost path to W is 3, and the predecessor node is Y. Right? So that means that to get to W, your cost is going to be 3, and the predecessor node for that is going to be Y. that still doesn't tell me where to send the next packet here. So then what you do is you look at this predecessor node and see the shortest cost path to that predecessor node. So Y is the predecessor node. Now you have to see how to get to Y. You get to the data structure for Y. You see the cost is 2 and the predecessor node is X. So now you're going to update your table here because X is a direct neighbor. That if any packet is intended to go to W, then it has to go through X. And X will fill its routing table and it'll have Y. So an important property that's used in this mechanism is that if you have this path U, X, Y, W, which is the shortest cost path, then an important property that's used is that U, X, Y, a subpath, is also the optimal path. So a subpath of the optimal path is also going to be optimal. This is a very important property of Dijkstra's algorithm. The algorithm is based on this important property. That's why you can build the paths iteratively. So the property is so if you are going to follow the path U, X, Y, W to W, that means that your path to Y is going to be the subpath U, X, Y. U, V, Y cannot be optimal. So all subpaths of an optimal path are also going to be optimal. You had a question or? So now there are some issues with this algorithm. First, if you look at the complexity, at each iteration you have to check all nodes W which are not in N. So the approximate complexity of that is order N square. You have better, more efficient implementations which bring it down to N log N. The other subtle issue with this algorithm is that it can cause oscillations. So remember when we have designed this mechanism, when we compute the routes, we assume static costs for each of the links, right? So your routing algorithm will then give you a best path to a particular node, and then your forwarding mechanism will send all traffic along that best path to that end node. The effect of that is, if there is more traffic being carried on that best path, then that path may not remain best for too long. If your metric is loss or delay or the available throughput, then all of them are related to the amount of carried traffic. Yeah.
The cost
The cost can be dynamic, yeah. So you have to think about the algorithm, how fast you want to update, and how stable is the routing algorithm. So the simple example is depicted here. You have a 4-node network. Nodes D and B are sending 1 unit of traffic to node A. Node C is sending a small amount of traffic E to node A. Once you go through Dijkstra's algorithm and you compute the paths, node C will probably choose this path or this path. It doesn't really matter. Both paths have cost 1. Now your link cost in this example is exactly the amount of traffic carried. So when D and B join the network, they have a direct link to node A, and so they have only one path available at that point. The cost is going to be 1 for both. So now when C wants to send traffic, it's looking at 2 different paths. Both paths have 0 plus 1, a cost of 1. It chooses one of them. It could be this one. Now the cost of this path becomes 1 plus 2e. Right, because E is going through this path. As soon as that happens, C will realize that it has a better path available here. So it's going to shift its traffic from this path to this path, because the cost now here is 1, whereas the cost here was 1 plus E. B also realizes the same. So look at B. Now what is the cost of B, of this link, B, of this path from B to A? It's going to be 1 plus E, which is the amount of traffic carried here. But look at this path that B sees now. So the cost of this path is 0. Nothing is flowing in this direction. 0 and 1. So now B is going to shift all its traffic to go through this longer path. Now the cost of this path or this link becomes 2 plus E. Both A and B, or both D and B, notice that, recompute the best path and send traffic along the other path. And this is going to happen over and over again, and there will be oscillating routes. So this is actually a phenomena which can be observed in practice. And we'll look at ways you can avoid that. So the Bellman-Ford algorithm is a distance vector algorithm, which is a distributed way of computing these best routes or the spanning trees. And the Bellman-Ford equation also depends on the same property. If you have dx comma y, which is the cost of the least cost path from x to y, then that minimum distance or the optimal distance is the minimum of the optimal distance to a node V and the cost between that node V and this node X. So What do I mean by that? See, this is the optimal path. To a node y from x. Now you look at all your neighbors. So x will have a bunch of neighbors, and all of them have their own optimal path or least cost path. Then your least cost or your optimal path will contain a subpath which is optimal plus a cost which is going to be minimum. So the sub cost of this path is also going to be optimal, and this is the same property that we had for Dijkstra's algorithm. So you minimize over all the optimal paths available. Look at your minimum cost to all of those optimal paths, and then choose the one that minimizes that cost. Now again, if we go back to the same example as we looked at for the Dijkstra's algorithm, you have this node U. You're trying to compute the best path to node Z. Then what the Bellman-Ford equation says is that your optimal cost path is going to be the minimum of over all your neighbors V, X and W of the optimal cost path, optimal path cost of those neighbors plus your cost to those neighbors. So what does this imply physically? When you have to implement this algorithm, what do you need to know at a particular node? In the case of Dijkstra's algorithm, you had to know the entire topology, the entire link costs and all the connectivities. Now here, all you have to know is for each destination node, you have to know what is the optimal path cost for each of your neighbors to that destination node and your cost to that neighbor. So all the information that is needed to compute here is local information. You need information only about your neighbors. What is your cost to the neighbors and what the neighbors tell you is their best cost to a particular destination. So all information that is required here is local. Once the neighbors can give you the right cost, then you can compute the best path and populate your routing table. So now the question is, how do the neighbors compute this? Well, they are going to use a technique similar to what you are going to use. They are also going to look at their neighbors, compute their optimal path cost, and then propagate that information back to you. The difference between Dijkstra and Bellman-Ford is that these quantities are going to be used by the node U as information that is coming in from the neighbors. In Dijkstra's algorithm, U itself was computing these values. Now you will be given these values, and based on these values it will compute the best path. Yeah.
Backwards from node Z because because if you need to find DUZ, you need to know DBZ.
Right.
And to know DBZ, you need to know, I guess, its neighbors to Z, or not happen to Z.
Right. So what the way it runs is that it's all of these nodes are going to do some computations based on the local knowledge that they have. Once they have some new information, that new information is propagated to their neighbors, and then everyone does computations again. So this algorithm converges over a period of time. In Dijkstra's algorithm, after k steps, you knew the best path and the cost to k destinations. Here there is no guarantee, but as the algorithm runs, it will converge to a solution. So let's stop here, and in the next lecture we'll go through the details of the distance vector algorithm.